So good afternoon, everybody. So this afternoon, it's my pleasure to welcome Dr. David Blewett to the TEPS seminar. Dr. Blewett is an expert in remote sensing analysis of airless bodies, particularly the spectral analysis. So he got his PhD from the University of Hawaii in geology and geophysics and is now a principal professional staff at the Johns Hopkins University Applied Physics Laboratory. While there, he's participated in many NASA-funded projects. He served as a participating scientist on the Messenger mission to Mercury and the Dawn mission to Vesta. I met Dr. Blewett in 2009 when I started my postdoc at APL, and he was the inspiration for my interest in lunar swirls. And we actually wrote a paper together about lunar swirls using mini-RF radar data. And now, years later, he's serving as the principal investigator for the Lunar Vertex mission, which is headed to the Reiner Gamma lunar swirl, which is one of the most beautiful and iconic swirls on the lunar surface. Hopefully, and Dave, update me if I'm wrong, this will be delivered to the moon using a NASA-provided commercial lander in 2024.
That's right. Yep.
All right. And so he's going to tell us more about this mission and hopefully a little bit of the background on the lunar swirls today. So take it away.
Okay. Let me get the screen broadcasting going. Yeah, thanks, Catherine and Ahmad, for the invitation. It'll be fun to talk to you guys. How's that presentation look on your screen? Looks good. My sound is good. You can hear me. Okay, great. Yeah, so the title is Lunar Vertex, a PRISM mission to explore Reiner Gamma. So first I'm gonna talk about PRISM, what that is, and then I'll talk about why you would wanna send a mission to a place called Reiner Gamma on the moon. I thought I would just mention a little bit about my affiliation about the Johns Hopkins Applied Physics Lab. You've surely heard of Johns Hopkins University, which is pretty famous for its medical school in particular. The university is located in the city of Baltimore, here in the state of Maryland. APL is affiliated with Johns Hopkins. We're part of the Johns Hopkins universe or whatever. But APL is located in a town called Laurel in suburban Maryland, about 20 miles away. So there's about 7,000 people who work here, most of whom are engineers working on defense-related R&D projects. So the average APL staffer, we don't have any affiliation with an academic department at the university. We're not faculty or professors. But within the space sector, there is a branch called the research branch. And within that, there is a space physics, heliophysics group, a group that's interested in the upper atmosphere, the ionosphere, and my group, the planetary exploration group. Can you see my cursor dancing around there? Okay, good. Yeah, so we function more or less like a university, geology or physics or astronomy department, except that we don't teach, and we generally don't have graduate students, though occasionally there's a joint grad student with someone in a department at the university. So we're kind of just a soft money shop, and of course APL builds a lot of space missions, so there's an opportunity to be involved in those. Okay, so yeah, I just wanted to make clear the APL, Johns Hopkins. It's probably analogous to Caltech and JPL, right? The average JPLer is not a Caltech professor, All right, so we're going to be talking about the moon today. I know this is an exoplanet seminar, and the moon's not very exo, but I understand you're interested in space missions, and this is kind of a new paradigm for flying missions to the moon anyway. So hopefully we'll hold your interest here. All right, so what is PRISM? Well, it's a new program that NASA was just introduced in 2020 And what it is for suites of science instruments that are placed on the lunar surface by a commercial lander. NASA has this other relatively new program called CLPS, Commercial Lunar Payload Services, that is for lunar landers to commercial companies to build landers to go to the moon. In the first solicitation, which you see a piece of here on the screen, NASA decided that there would be two deliveries, which have come to be known as PRISM 1A, which is going to Reiner Gamma. That's what I'm going to talk about. And they also solicited at the same time a second mission to go to the Schrodinger Basin on the far side of the moon. And here's the key information. So I mentioned it's a low-cost program. So you can see that they allocated $60 million for these two deliveries. And they didn't really specify, like it's 30 million for one and 30 million for the other, but that's kind of what we had to assume in our proposal. Like we probably could have tried to get 38 million out of them, but then you kind of risk, oh no, well, what if they're gonna, say no because it's too expensive, so there's all these trade-offs. Our delivery could total 50 kilograms in mass, and that has to include everything you want, for your scientific instruments. If you wanted to have something like a sample arm, you have to account for the mass of that. Or in our case, we have a rover, so we had to account for the mass of the rover within this not to exceed total of 50 kilograms. And yeah, again, the lander and the launch are government furnished via this CLPS program. So here's some more about PRISM and CLPS, right? So the CLPS company is responsible for the entire end-to-end activity, right? They've got to integrate, accommodate, transport, and operate the NASA payload. They've got to go out and get a launch vehicle somewhere, buy a ride on a rocket. They have to build or provide the lunar lander, any surface systems. They're responsible for communications between the moon and the Earth, because these missions are not using the NASA Deep Space Network, which is used to communicate with most of the planetary and heliophysics missions. So the whole deal. The first 10 of these CLPS missions, the target destinations have been chosen, and I'll show that on a slide in a minute. And these are launching between this year and around 2026. Now, the really interesting thing, and it takes some getting used to, is that the lander solicitation is issued after the selection of a PRISM science investigation, right? So, normally spacecraft are kind of built custom, right? Where the spacecraft design is an inherent part of the mission. But here we've got this model where there's a commercial lander. And so a company has sort of their standard model lander. And okay, they're going to build to take a certain set of instruments from PRISM to the moon. And, they promise to accommodate all the needs that the science mission requires. But you can't really ask for anything too crazy, right? Because they want to, build their standard lander with essentially minimum modifications. But we did have to come up with this big list of accommodations in a thing called Appendix A that went into the request for proposals that went out to the CLPS companies, right? So fields of view, things like that. So say, we want to have a camera and it needs to be mounted at least 2 meters off the ground, and it has to have an unobstructed horizontal field of view of 40 degrees. Or in our case, we've got a solar wind spectrometer, and we can't have the spacecraft charging up and these electric fields deflecting the particles that we're trying to come in that we're trying to measure. So we levied requirements on the grounding of the spacecraft and that sort of thing. So all that went into this Appendix A, and then NASA put it out to bid. And 5 months after we were selected, Intuitive Machines was selected for our delivery. But yeah, there have been 14 of these companies that qualified to bid on these task orders. You can see their logos here. So there's some big kind of legacy aerospace companies like Lockheed Martin, big newer aerospace companies like Blue Origin and SpaceX, and then smaller companies like Astrobotic and Firefly and Maston and Intuitive Machines. And I'm told that of the, I think 10, anyway, there's of these 14, there's a few of them that actually haven't bid on any yet. So here's the CLPS deliveries that are coming up in the next few years. The first one is going to be this Intuitive Machines mission to a place here kind of between Oceanus Procellarum and the Imbrium Basin. That's supposed to go relatively early this year. They had a launch slip because of the launch provider. There's another one going to go in 2022. That one's from Astrobotic going to the Lacus Mortis. There is a Firefly delivery going to go to Crisium in 23. Then, in late in 2022, there's going to be a South Pole delivery also from Intuitive Machines. So when Intuitive Machines was selected for our Reiner Gamma lander, we were pretty happy with that, because they've got 2 chances before our mission to learn how to land on the moon. So we think that's really good. Yeah, then there's a few others. The PRISM 2 landing sites have been designated, but NASA has not even selected the PRISM 2 science PRISM payloads yet. And then after that, they'll put out the bid for the CLPS deliveries to the Gruithuisen domes and to this another South Polar location. All right, so that's all about PRISM and CLPS. So now on to what's Reiner Gamma? Why would you want to go there? Well, it's just an incredibly beautiful feature, I think. On the left, you see a multicolor presentation with the sun high overhead, which emphasizes the inherent reflectivity or albedo differences of materials on the surface. And then on the right is an image with a lower sun illumination. So there's shadowing and shading, gives you an idea of the topography and texture of the surface at Reiner Gamma. So Reiner Gamma is the archetype, the most famous example of a lunar swirl, right? And it was seen in the earliest telescopes, hundreds of years ago. And at first, people actually thought it was a crater, and it was given the name Galileus, for Galileo. But later on, people realized it isn't a crater, and so the name Galileo was reassigned to a nearby, fairly unimpressive nearby crater. But telescopes improved. People realized that the tail doesn't really look like a normal crater ray, and it's not a ridge of highland material because it doesn't cast a shadow. So that's unusual. Then photography became available, and people were able to study these things in a bit more detail. And again, here's a pair of images from the rectified lunar atlas. Again, one at high sun, emphasizing just inherent albedo differences, and one at lower sun, where you can see the topography. And it really became clear that Reiner Gamma is just a superficial high reflectance marking. As far as you can tell, it doesn't have any topography of its own. And I just love this picture here on the lower right. Look at that, Mount Wilson, 1920. So the picture is over 100 years old. So yeah, so this strange marking was named Reiner Gamma. This is the crater Reiner, just there. So the albedo marking was named Reiner Gamma, and it's of unknown origin. Well, then the space age happened, and we found out that there are swirls on the far side of the moon. Here's a picture from Lunar Orbiter 2 in the mid-60s. These are some really spectacular swirls in Mare Ingenii on the far side. Then a couple years later, Apollo 8, the first time humans went to the moon and made a few orbits, the astronauts stuck their camera out the window and took this really beautiful picture of the swirls near Goddard A crater and across Mare Marginis. And then a little while after that, also from pre-landing Apollo, was Apollo 10, the astronauts took this picture of swirls near the crater Firsov. And these swirls are in the highlands. So, the Reiner Gamma is on in Oceanus Procellarum in the lunar Maria. Most swirls seem to be associated with the Maria, but indeed they can be found in the highlands as well. Then another thing that happened during Apollo was that Apollo 15 and 16 released subsatellites that had magnetometers on them. And so these were in near equatorial orbits, but they did discover that Reiner Gamma is associated with an area of enhanced magnetism. And these things came to be called magnetic anomalies. So here's a figure from this 1979 paper in Science that showed the correlation between the magnetic anomaly and the swirl. So wow, that's a surprise. What's going on with these two things, and how are they related? So later there was orbital mapping of the magnetic anomalies from polar orbiting spacecraft like Lunar Prospector. This is a map of Lunar Prospector magnetic field data here. So it's a puzzle, right? I mean, the moon today is a planetary body that doesn't have a global magnetic field, but it turns out it's got these localized patches of magnetic crust, and the origin of the magnetic anomalies is unknown. All right, so now I'm going to kind of switch back to talking about the swirls and the hypotheses for where they come from. So probably the hypothesis that has the most support, I would say, is solar wind standoff. So the idea here is that the presence of the local magnetic field acts as kind of a little umbrella, right? The magnetic field deflects the incoming ions from the solar wind that reach the surface in normal non-magnetic areas, and that this slows down or stops the normal soil darkening process or space weathering, as we call it. And I've got a slide talking more about space weathering in a minute. But the idea is that the sputtering and implantation caused by these solar wind protons affects the surface, but that doesn't happen under the magnetic bubble. Then there's a class of ideas related to comet impacts. Okay, the first of which comes from Pete Schultz and his collaborators, and it has to do with the action of the gas and dust in the coma of a comet, modifying the surface, a kind of a hurricane wind, almost, that modifies the surface and exposes fresh material. Then there's kind of a variant on that favors more kind of the solid material, nucleus fragments or swarms of meteoroids that plow up the surface and expose fresh material from some, moderate depth beneath the surface. Then there's a set of more recent ideas that have to do with kind of levitated dust behaving strangely. The idea here is that the presence of the magnetic field can lead to induced electrical fields, and that these electric fields may influence the behavior of little levitated dust grains that get charged up because they're of solar UV. And these little charged dust grains are, hopping around, and they may be either attracted or repelled from certain locations. And so there may be accumulations of fine high reflectance dust, or maybe that this unusual dust activity modifies the very uppermost texture of the surface, the so-called fairy castle structure, this super highly porous structure that can exist, in a vacuum. And that's why swirls are bright, because of these different photometric effects, related to porosity and things like that. Or maybe even there could be actual magnetic sorting of little moving dust grains based on their metallic iron content. Okay, so here I'm going to talk a little bit more about space weather, right? So here, let's consider two craters, essentially the same size. They're both in the central near side highlands. Okay, now on the left, we've got Tycho, right? One of the probably the most famous crater on the moon, one of the most famous. It's morphologically fresh, right? If you look at its walls, its rim, the central peak, they look sharp. There are very few, if any, superposed craters, that have formed in the time since Tycho formed, and Tycho's got extensive rays. Now over here on the right, we've got our buddy Pitiscus. Okay, its rim and walls have been rounded down. There's hardly anything left of the central peak, and there's some fairly sizable craters that have formed on top of it. Right, so clearly Pitiscus is older. It's been exposed on the moon to impact cratering for a longer period of time, and so it's older, and also it doesn't have rays. And that's really emphasized here. If you look at this, kind of full moon type photograph, there's Tycho with these rays that go, halfway across the near side, and it's like, okay, well, where's Pitiscus? Well, it's pretty hard to see because it doesn't have prominent rays. So because we've got these younger craters have bright interiors and rays, older craters don't. So something must be going on that causes the rays to fade away with time. Otherwise, no craters would have rays, I guess, right? Because the fresh material dug out of an impact and deposited across the surface would have the same albedo as the background material on which it was being deposited, right? So there's some, darkening process that takes place with time. And we call this space weathering. And, space weathering affects surfaces of the airless bodies, all through the solar system. And it makes it harder to interpret remote sensing data. If you're really trying to figure out, the composition of a remote surface, well, there's this, weird modification that's gone on that decreases the contrast of absorption bands and makes the surface darker. Now, the general wisdom is that space weathering is caused by solar wind exposure and micrometeoroid bombardment, right, which can cause melting, vaporization, and so forth. But we don't really know the relative roles of these two things. However, at a lunar magnetic anomaly, we've got this perfect natural experiment, right? Because we got a control on one of the variables. The magnetic field is not going to influence the flux of micrometeoroids, but it does attenuate the solar wind. Okay, so that's like swirls, and maybe where do they come from? Now, there's this separate mystery, right? Which is, why is the magnetic anomaly there in the first place? All right. So one idea has to do with magnetized basin ejecta. All right. A basin is just a big impact crater. On the moon, any crater that's bigger than maybe 200 or 300 kilometers in diameter, we call a basin. And the idea here is that during the formation of a large impact basin, any ambient magnetic fields could be amplified by compression as an impact-generated plasma kind of converges on the antipode of the basin. And a number of the magnetic anomalies, so here's a global map, kind of with garish colors. A number of the magnetic anomalies are found antipodal to large basins like Imbrium, Crisium, and a few others. All right, so then another idea for the origin of the magnetic anomalies is the idea that wants to make the swirl and make the magnetic field in the same event, which is the impact of a comet's coma on the moon. And again, here it's posited that there are plasma interactions, from the plasma in the coma, and this is, compressed against the surface, can be amplified, and it magnetizes the surface during that impact. Yet another idea has to do with, well, maybe the moon did have an internal, dynamo field in the ancient past, which has since died away. But if there were lava flows or intrusions of magma or even impact melts that were formed back in those days, and that they cooled through their Curie temperatures in the presence of those fields, that they could retain a magnetic signature. And so what we're measuring today is a remnant magnetic field. And then there's also an idea that, well, there could be an influence from debris from an iron-rich impactor, right? So this kind of gets to, well, what's the carrier of this magnetism, in the lunar rocks? Maybe there was an iron-rich asteroid, most of which probably would have been vaporized in an impact. But if it was an oblique impact, anyway, there's probably going to be some iron, nickel, metal strewn about and incorporated into the impact deposits in some form or fashion. Okay, yeah, so here back again to the map of the major magnetic anomalies. The strongest anomalies have an amplitude of a magnitude of about 20 nanoteslas. Of course, this has, again, only been measured at orbital altitudes. And downward continuation, you can kind of extrapolate that they might have strengths of 100 or 1,000 nanoteslas on the surface, but we don't actually know. So this is why it's important to get down on the ground and actually measure that. But another thing that these magnetic anomalies do is that they change the moon's interaction with the solar wind as the moon goes around in its orbit. So, much of the time the moon is out in the solar wind, but there is part of the time when it's somewhat shielded from the solar wind in the Earth's magnetotail. And there is this near side, far side dichotomy, because, it's during full moon that the a moon is in the magnetotail, so there's a somewhat attenuated solar wind exposure on the near side. But these local fields, they change, what would happen from what if the moon was just a dielectric silicate rocky sphere, right? It's got these local magnetic fields, and data from various orbiting spacecraft show that there are, in fact, standoff regions that are formed over the stronger magnetic anomalies. In other words, mini-magnetospheres. So these have been documented through, measurements of reflected electrons, changes to the solar wind flow, reflected neutral atoms, and so forth. People have also done, a fair bit of modeling of this sort of thing, embed some dipoles in the lunar surface and, see what happens to the solar wind. But again, we don't actually know the actual flux and the energy of the ions and electrons that actually, make it down to the ground. So I think the magnetic anomalies are just great natural laboratories. There are places where we can, examine key questions in several major areas of planetary science. And I think there are, problems that bring together what Don Wilhelms in his book To a Rocky Moon called sky science, right? That's the particles and field stuff that was the earliest discoveries of the space age, right? I mean, discovery of the solar wind, discovery of the Van Allen belts, that sort of thing. But here in the on the moon in these magnetic anomalies, we bring together that sky science with actual, geoscience, planetary geology, the actual, rocks. Oh yeah, and as I mentioned, we get a control on one of these variables, the degree of solar wind exposure. So, these are places we can go, and relatively conveniently in a relatively small area of the lunar surface, you can do a lot of really cool studies, right? Related to geophysics. Okay, what's the nature and origin of the magnetized crust? Was there an ancient dynamo? Were there magmatic intrusions? What about this idea of magnetized basin ejecta, comet impacts? Certainly comets, have hit the moon in the past, and there's all this like weird magnetic effects going on. Then there's the space plasma physics, mini-magnetospheres. There are magnetospheres throughout the solar system, and we've got, as part of that diversity of magnetospheres, we've got these, little ones on the moon. So that's of interest to space physicists. And then there's all the geology and surface processes, space weathering, solar wind implantation, what's the origin of the swirls? Can the proton implantation contribute to the lunar, hydration cycle? Dust motions that may take place, comet impacts, and maybe there's unusual rock types that've got high metallic iron contents. So I and a number of others had been advocating for the scientific wonderfulness of a mission to a magnetic anomaly for some time. So we were pretty happy when we found out that NASA designated Reiner Gamma as the target site for the first PRISM mission. So my pestering and had paid off apparently. So at APL we wrote a proposal. That's the cover of it there. And the three science goals of the proposal were to investigate the origin of magnetic anomalies, investigate the origin of lunar swirls, and determine the structure of the mini-magnetosphere that forms over the Reiner Gamma magnetic anomaly. And then in the course of doing those things, we sort of for free, do these other things, right? Which is help to understand, the two agents of space weathering of the silicate regolith, right? The micrometeoroids versus the solar wind implantation. And then there's also certain so-called strategic knowledge gaps for human exploration that we can contribute to a little bit. Now, NASA got 12 other proposals for the Reiner Gamma mission. And so we were, really fortunate that ours came out on top. So in order to address those science goals I just mentioned, we had a science traceability matrix that, shows how you go from the questions, to what measurements do you ought to make, and then what instruments do you need to make those measurements. So here I'm going to talk about our instruments. We've got 3 instruments that are going to be on the lander. So the first is an array of cameras. These are used to, provide geologic context of the landing site, and also to perform photometric modeling in other words, to study the manner in which the brightness of the surface changes as the illumination angle changes, as the sun moves across the sky. And that can be related to physical characteristics of the surface, the porosity and particle size and so forth. We are going to a magnetic anomaly, so you bet we've got a magnetometer. We're calling this one VML, Vector Magnetometer Lander. So this, you can see a diagram of it here. It's got a primary science grade flux gate up at the top. And then we've got this tetrahedral array of commercial mini magnetometers down at the bottom that help to separate any fields from the lander from the actual natural field that we want to measure. And, this is important, especially because, we didn't get to fully specify our own perfect magnetically clean lander, right? We're kind of going on this more or less pre-designed lander. And one key thing is that this magnetometer is going to operate during descent. It's the only one of our instruments that's going to operate during descent to the surface of the moon. So that profile with altitude will be really important in constraining the nature of the magnetic source body. And then we have a plasma spectrometer. So this is an ion electron spectrometer. It's going to measure the energy and flux of ions and electrons that actually make it down to the ground. Oh, and I should mention our partners. Yeah, so Southwest Research Institute's building the solar wind spectrometer. A company called Redwire in Colorado is building our cameras, and APL is providing the magnetometer. Now we've also got a rover, and we have to pay for the cost of the rover out of our budget, but we really need to get away from the lander to accomplish a number of our science goals. So a company called Lunar Outpost in Colorado is building our little rover. It's only about a little over a foot tall. It's got stereo cameras in the front for navigation. It has sort of a LiDAR thing to help it avoid rocks or holes in the ground. But essentially, it's going to operate where a human operator sets out waypoints, and then the rover executes them. So the rover is going to carry two instruments. One is a copy of the magnetometer, the lower part, just the 4 commercial mags. And then in its belly, it's going to have a close-up imager that's going to look down at the ground so we can determine the texture and composition of the soil immediately beneath the rover. So it's important to get away from the area of lander disturbance so we can look at the pristine swirl. So our landing site is going to be near the northern edge of the main Reiner Gamma bright swirl area, and we're going to traverse generally north towards the so-called dark lane. You can see a candidate traverse path here. We need to have line of sight between the little rover and the lander, so we use these viewshed maps to help us choose our traverse path. This is the actual landing site. These are the coordinates. It's a nice smooth area. We're not trying to land on a crater rim or central peak or anything, so it should be easy for the lander to get us down safely. This is the org chart. APL is responsible for the project management, systems engineering, safety and mission assurance, science, and the payload. I talked about all the instruments, and then we're going to integrate the 2 of the instruments into the rover here at APL, do the thermal vac, and then we deliver that to the lander. This is our science team. We've got a nice mix of younger people and more experienced oldsters like me. We have a number of foreign collaborators. And you may have noticed, if you were paying attention, we've got quite a few Canadian connections. Canadensis Aerospace, they're in Bolton near Toronto, is building our rover multispectral microscope. Miriam Lemelin from Sherbrooke is a co-I, as is Ed Plutus from out in Winnipeg. Okay, so I just thought I'd mention our mission name, right? In Latin, the word vertex can mean swirl, which is good. We're going to the most famous lunar swirl. But in English, a vertex is an intersection, So I see it as kind of the crossroads of geoscience and particles and fields domain of space physics. So this intersection is sort of our theme. It's a highly interdisciplinary mission. So yeah, just to end up, I'll just say Lunar Vertex is the first PRISM mission. We're going to go explore this unique environment of a lunar magnetic anomaly. We're going to address a bunch of cool questions in various subfields of planetary science. geophysics, space physics, planetary geology. We're going to hopefully go a long way towards solving the mysteries of the origin of lunar magnetic anomalies, the origin of the swirls, the interactions of the solar wind with magnetized crust. Launch is scheduled for April 2024. And with that, I'm just going to go on to a neat video from the NASA Goddard Scientific Visualization Studio that zooms in on Reiner Gamma. And we'll just play this in a loop, and we can take any questions as this runs. So hopefully it won't be too herky-jerky over the interwebs, but you can see the near side of the moon rotating around there, Western Oceanus Procellarum, zooming in on Reiner Gamma. In a second here, it's going to tip over into an oblique view, and you'll be able to see kind of the an oblique view looking generally generally west, with the lunar horizon in the background. So anyway, that's where we're going. It's just incredible that we're going to be there, in like less than 2.5 years. So that'll be it. Thanks, and I can take any questions.
We do have some time for a few questions. Does anybody have any questions? Feel free to just unmute yourself and ask, or if you want to raise your hand, you can raise your hand and we can call on you.
Well, I'll start to kick things off. So at the beginning of your talk, you mentioned that you were glad that, is it Innovative Machines?
Intuitive Machines.
Intuitive Machines. It was going to have a couple of practice runs under their belt. Are you? Yeah. Are you, however, worried they might be delayed on your mission because they're too busy doing these other 2 missions first? Is that a concern?
Well, we have a call with them every 2 weeks. Intuitive Machines is located in Houston, and apparently was founded by some ex-Johnson Space Center engineers, and they seem to be totally on the ball. Yeah, I think the experience they've gained, from working on the first 2 landers has really gotten them quite a good way. Incidentally, they selected SpaceX for the launch. It's going to be on a Falcon 9, and apparently Intuitive Machines bought the entire manifest on that Falcon 9 launch, so that we won't have to worry about being delayed by some other paying customer payload that was going to also, be deployed during that launch. So I think that's good. Yeah. Yeah, they have venture capital money. Sorry. Yeah, so I'll get to in just a sec. Yeah, they have venture capital money, and yeah, they seem to be totally on the ball. And compared to our minuscule budget that we have, we're almost having trouble keeping up, with Intuitive Machines, because they're just bang, bang, bang. Obviously they want to make money, yeah, and they bid fixed price contract, right? So there's not if we have some major change, it turns out we gotta, our payload's going to be 1.5 kilograms heavier than we thought. They could by rights say, well, okay, pay up, right? Because we only agreed to ship 30 kilograms of your stuff to the moon, not 31.5. Okay, sorry, go ahead, Simone, it looked like.
Yeah, I was just curious, you mentioned that there were, I think, 12 other proposals for the same area. Yeah. What were they? Would they have been studying the same thing, or would they have been branching out?
Well, the announcement from NASA said that you had to address science that's uniquely accomplished at Reiner Gamma. So they would have been, presumably looking into the origin of swirls and the origin of the magnetic anomaly. You know, for this mission, you couldn't just propose, you know, like just something that could have gone anywhere on the moon.
Okay,
So,
that makes
yeah.
sense. That was kind of what I was wondering. Yeah.
Right, right.
Thank you.
Sure. Although I will say that there are other payloads on the lander besides Lunar Vertex, right? I mean, we consider Lunar Vertex to be the primary payload because it's, you know, intended to go to Reiner Gamma. But NASA also has a list of stuff that it has been looking for a ride to the moon. And so it put some of those on our lander. And these include, there is a laser retroreflector from the European Space Agency for laser ranging between the Earth and the moon for, you know, dynamical studies. There is a solid state high energy particle detector from the South Korean Space Agency. And then there is a package, a technology demonstration from the NASA Space Technology Mission Directorate, which is different than the Science Mission Directorate, which is funding our work on Lunar Vertex. That is a JPL tech demo that has 4, count them, 4 rovers that are going to go off and do some robotic cooperative interaction thing, mostly with close by to the lander. So these missions, they're kind of sort of Christmas trees, right? I mean, because who knows what else. And then Intuitive Machines, if there's mass left over, they could sell it to, you know, I don't know, whoever, right? I mean, the, you know, inflatable Taco Bell, you know, advertisement or something, right? Who knows what it could be if there's mass left over. But there is a do no harm clause that the inflatable Taco Bell billboard can't interfere with any of the actual science.
Do we have any other? Oh. Sorry. Do we have any other questions?
So how is the rover going to be tethered to the lander? How are they going to communicate?
Yeah, it's going to be S-band radio. So yeah, the rover has a little sort of patch antenna on the side of it, and the lander is going to have an antenna up towards the top. It turns out that the you know what, maybe I'll stop this, and I do have a picture of the lander that I'm allowed to show. Let's see, how can I get to there? So the Intuitive Machines lander is quite tall. We had kind of had in our minds, you know, a lander that might be maybe 2 meters or something, but it looks like the antenna is going to, whoop, did I accidentally switch something?
Yeah, I saw it there for a minute, and now you're back to your PowerPoint presentation.
Okay, sorry. What happened? Oh, my screen's frozen. Oh wait, here we go. Is it back?
Yeah.
Okay. Yeah. So the lander is pretty tall. We were kind of expecting something of, you know, Astrobotic and some of the others, their landers are a bit more squat. And so it looks like the antenna is going to be about 4 or 5 meters high off the ground. And we did all our view shed maps for assuming 2 meters off the ground. So it should be, we should have better line of sight, but to the rover. The rover is supposed to be smart enough that if it drives into a place and loses line of sight to the lander, that it can turn around and come back to the last point where it had communication. And then, you know, we could presumably pick a different waypoint for it to go around a little, you know, swale or crater or whatever. Right, so these gold boxes you see here in this view, those are the JPL rovers, and they're just going to deploy by dropping straight down about 1 meter to the ground. But you can't really tell in this view, but the gold box here our rovers in there. And we required them to deploy us within 10 centimeters of the surface. So there's actually kind of a garage here. And there's this arm that's going to kind of fold down like that. And our rover, you know, is inside there, and it's going to come down, and its base plate is going to be deployed within 10 centimeters of the surface, maybe onto the surface, so that we can fire our launch locks, cut the 0 force umbilical connection to the lander, and then drive off. And we've got to get into sunlight quick, so that our solar panels can start, you know, generating power. Yeah, this thing, let's see, I think this is the European retroreflector. This is our ion electron spectrometer. They built a little balcony out to the side to get the field of view that we need, because we want to have a view of like essentially the whole sky, because the charged particles might be coming in from pretty crazy angles, having been deflected by these local complicated magnetic fields.
Well, very cool. It is an unusual lander, and I look forward to seeing it deployed on the moon. I think that's it for questions, but I guess just thank you for your time. I enjoyed learning more about this mission, and I really am looking forward to seeing the results.
Oh, sure thing. Yeah, appreciate talking to y'all. You going to go to the LPSC, Catherine?
Not this year. I still have an unvaccinated kiddo at home, so I'm waiting.
Yeah, I'm actually gonna make the trek. I decided it'll be interesting. It'll be the first time on an airplane in more than 2 years. So
yeah, it's interesting.
Yeah.
All right. Well, thank you again, and perhaps I will see you at a future meeting when the world is a little less crazy.
Yeah, for sure. And I hope to make it up to Canada.
Yes.
Again at some point.
Well, we're having a meeting here in October. If you'd like to join us for the DPS meeting.
Yeah, and we may go to visit Canadensis. So
fair enough. Yep.
Maybe maybe in Toronto at some point. Yeah.
All right. Thanks again.
Okay.
Bye.
Appreciate it. See ya.